Okay, so our topic for today is basic characteristics of bipolar junction transistor BJT. We'll be studying the basic characteristics of a transistor, essentially a bipolar junction transistor. You must have studied the semiconductor physics behind BJT. So we'll start with the characteristics. This is a basic circuit. See, what are these? This is an NPN transistor. This is the base, B stands for base, C collector, E is emitter. This is the sign for grounded. This is grounded. The emitter is grounded. Therefore, this is common emitter. The emitter is common amongst all these devices. The transistor, resistor, the power source. So this is common. That is, emitter is common. So this configuration is called common emitter. Common emitter CE. We have three such configurations: CE, CB, CC. For common emitter, common base, common collector. This is common emitter. For explanation. Okay, so this is this. What is this? I'll start from this side. This is the load, and this is VCC. That is the power that drives the load. It is a DC source. This connects to the collector. This is NPN. Okay, so the flow of current is from this to this side and from this to this side, P to N side. This you know. This is base. Now come to this side, the input side. We have RB and we have a base voltage. Why? This is to bias the PN diode of this part. See, this current actually biases the PN diode. Clear? How it biases, you know, you must have studied diode. So this is provided for biasing this PN junction so that current flows. And what is this? This is the signal. This is the signal. Why are transistors used in C configurations? Mainly for amplification. What is amplification? Amplification is amplification of current. If this is, let's say, IS, this source is generating a current that is IS, then we want an amplified version of this current at the output, that is across the load. Or if the source voltage is Vs, we want an amplified voltage at the output. So there is amplification of current, there is amplification of voltage, and amplification of current into amplification of voltage is power amplification. So transistors are used in C configurations mainly for amplification. How we amplify it? How is IS getting amplified at the output? That is what we have to understand. Let's understand this. This is NPN transistor. Clear? This is N, this is P, this is N. Now I am rubbing this and I am putting the symbol of a BJT. Let's see what it will be. It will be like this, then this, and then this. This is emitter, so we'll have this sign here. This is collector, this is emitter, and we put a circle across this symbol. So this is the symbol of BJT, that is bipolar junction transistor, NPN transistor. This is emitter. Clear? Now let's see what happens. We have this base voltage. Why? To bias this PN diode. Let's see how this is represented in a two diode analogy. It is represented as this. You must understand this to understand the functioning of a transistor. This is emitter, this is base, this is collector. This is called two diode analogy of this transistor. So this is forward biased. You can see the photo. You must have studied diode. So if you apply voltage greater than the threshold voltage to this, that is VBE, if this voltage is greater than the threshold voltage, we'll have a forward biased diode and current will start to flow. This is what? This is reverse biased. We have VCC, say the voltage is at this point. So this is positive, this is negative. So this is reverse biased. This is the the normal way in which transistors are biased, that the base emitter is forward biased and collector base is reverse biased. This is reverse biased and this is forward biased. This is the normal operation of a BJT. So now let's see how it amplifies. We are giving a voltage. Why? To forward bias this particular diode, this PN junction diode. Now, what happens here? Let's try to understand it. I am drawing the diagram here. We have, let's say this is our current, then IB, it is a DC current. If this is omega t, this is DC current, plane, clear? So if IB is from this point, it is like this, simple DC current. Second is, we have IS, this from the source, the AC source, this is IS. Let this source be like this, a sinusoidal source. Okay, this is IS, this is IB. What happens? This current that gets into the base is denoted as IB. These are conventional notations. IS, capital IB, small IB, these are conventional notations. You will find almost in all the books these notations are used. So if you add these two, what happens? This is equal to a current. This is our from origin. Now this is our IB. So this current actually rides over, if this is this, so this current actually rides over this DC current. So what we get is IS, sorry not IS, IB, this current becomes this. Clear? So the effect of this and this is, this current actually forward biases this diode and this current rides over that particular level of current. Clear? So this is first part. Now second part. The question is, when this collector base is reverse biased, you can see we have put VCC here. So this is reverse bias. When this is reverse bias, how can current flow through this transistor? How can we have current in this direction? The reason is, I am not going into detail, just you should keep in mind, the collector base junction, this is heavily doped. First is, it is heavily doped, and second, this junction is very thin. Clear? This collector base junction, this is heavily doped. Because of heavily doped, what you will have? You will have number of free electrons, more free electrons and holes. So this is heavily doped and the junction is very thin. What happens then? Because of this, the reverse saturation current, if you remember from diode, reverse saturation current, the avalanche and the breakdown current. So that current starts to flow, and that is the volume is very high, or I shouldn't say volume, the magnitude is very high. Reverse saturation current, the magnitude is infinite, you know this. So what happens? We forward bias this, and because of the particular configuration or manufacturing technique of this junction, reverse saturation current flows in this direction. So what happens? We have forward bias this, and we have an AC component in this particular direction. Because of this, an AC component of collector, that is IC. Initially what we had? We had IC. So now our current becomes this big C. This is small c, this is big C. Because of this IS, an AC component of collector current in the collector circuit actually starts flowing, and this is because of this particular design features, this is in amplified. This what we get is an amplified version of Is. That is, this is very large to this current in comparison to this current. Therefore, current gets amplified. And when current gets amplified, obviously IC plus IC, this flows in through the load. Therefore, the voltage will also increase because current has increased and resistor RL or whatever the load is, it is the same. So when current increases, voltage increases. Therefore, if the current gain is AI and current voltage gain is AV, then our power amplification, that is AI into AV, becomes large, and this way we are able to amplify this this signal. So this is the mechanism by which a BJT amplifies the input signal. This is clear? So I am writing the currents. This is IC, this is IC, this is what? IE. Obviously IE will be, we'll have to look into these things. IE will be, that is the DC plus AC component. So this will be equal to IB plus IC. This current plus this from KCL, Kirchhoff's current law. If this be node, this is entering the node, this is entering the node, this is exiting the node. So IE is equal to IB plus IC. This is first part. This voltage from here to here, from here to here, from collector to base, what we say, this is VCB. Okay, this voltage is from base to emitter, so VBE. Clear? And this voltage, this is from collector to emitter, so what this will be? VCE, which is actually equal to our output voltage. Clear? So these are the notations. Okay, now the doping of base emitter junction is such that a small current IB can control a very large current IC. I told you this IC is very large compared to IB. So our doping of the base emitter junction is done in such a way that this IB can handle a large value of collector current, because that will flow through this circuit. And from here you will see that IE is IB plus IC and VCE, this is equal to VCB plus VBE. That is I am writing it here, VCE is equal to VCB plus VBE. Clear? Now what happens? This PN junction, this particular PN junction, what it is doing? It is actually controlling this collector current. So it is acting as a gate or a valve for the load current. Clear? So our base emitter junction is acting as a valve or a gate for this collector current to flow. If we stop this biasing, this will stop, current will stop. If we will increase, this will increase. So we are using this junction as a valve. Clear? Keep these notations in mind, whatever I have written. Now I will start deriving, some parameters. Now let's understand these two graphs. This is very important to understand the transistor characteristics. See, this is called input characteristics. That is the base current versus base to emitter voltage. You remember the circuit, base to emitter voltage is applied and IB is the current, IB, that is generated from VBB. Okay. So you can see this is the typical characteristics of a diode. This is threshold voltage, after which the current starts to flow. Typically we have 0.6 volts for silicon and 0.2 volt for germanium. So obviously this is germanium. So after that threshold voltage, current starts to flow. Clear? So VB, IB up to 0.2 volts or 0.6 volt, whatever the case be, it is 0 and then current starts to flow. One important thing to note here is that for VC equal to 0, that is collector to emitter, if that voltage is 0, this will be the least. that is the voltage applied will be least for the same amount of current. As VC starts increasing, we will have to apply more base to emitter voltage. Why? Because of when you put this VC, it it affects the depletion region. So because of that, the graph is like this. So the more the larger VC is, you will have to put more base to emitter voltage to get the same level of base current. So this is input characteristics. Try to understand it properly. So let's understand the collector characteristics. It is IC versus VC. You see, for a small base current, this is our collector current. As we increase the base current, see, this is 0, this is 50 microamperes, this is 100 microamperes, and so on. What we see, as we increase the base current, the collector current starts increasing. Clear? So when I said that it acts as a valve, the base emitter junction acts as a valve, this is the meaning. See, when we are increasing the current, the base current, the collector current is increasing. One more thing to note is, this is in microamperes while this is in milliamperes. So you can see the current amplification here, milli by micro. So 10 to the power 3 we have here. So this is the way we are able to amplify current. So this particular, it's not, it's not up to the scale, or it does not, this figure does not represent any particular transistor. This is just for understanding. Actual sheets, if you will see the data sheet of actual transistors, it will be like this only. From here, what we do, if we have to find IC by AB, we take the value and put IC by AB. Or if we have to take for a small change in collector current because of a small change in base current, we can use these data sheets to find the results. So this is input characteristics, this is the output characteristics in the collector side. You must have understanding of this. Clear? Now we'll see what is collector cutoff current, ICEO. We have this transistor. Now if this is open, base is open, that is the current through this base is 0, IB is equal to 0. Then what happens? Our base to emitter is not forward biased. In that case, what current will flow in this circuit, that is collector to emitter? That will be the reverse saturation current. I told you earlier only that this is heavily doped and the junction is very thin. Which junction? Collector to base. So we have reverse saturation current flowing through, or the breakdown current flowing through this junction and through this circuit. So that current is called ICEO. That is current flowing from collector to emitter when the base is open. Clear? So this is ICEO. Clear? Now, let's say what is the DC current gain? DC current gain. DC current gain is written as beta DC given by IC by IB. Clear? Simple. Beta DC is IC by IB. This is DC current gain. Second is AC current gain. AC current gain is beta AC. It is given in change in the collector current because of change in the base current. This is the current by current. This is change in collector current due to a change in the base current. If we change base current from 5 microamperes to 10 microamperes, if the change in collector current is from 5 milliamperes to 10 milliamperes, then that gap by this gap is beta AC. Now what you have to remember, this is actually H capital FE and this is HFE, small fe. What are these? These are hybrid parameters. You will study when we will be dealing with small signal analysis, we will go through these parameters. For now, remember this is HFE. You will have this value given in all your questions. or in the data sheet. So HFE is beta AC and beta DC. For moderate, this is very important to remember. So I am writing for moderate collector current. What is the meaning of moderate? Moderate means that IC is neither very low nor very high. So for moderate collector current, our beta DC is almost equal to beta AC, that is given as beta, which is called large signal current gain. So from here we will have one equation for the current, that is IC is equal to beta IB, or to be more specific, this is actually equal to beta IB plus ICEO. This one, the collector current, cutoff current. So IC is this. You should remember this. We will be using it. Clear up to now?